Hello everyone, JoeKizis here with an update of our Highland project in western Nevada. It's a low sulfidation gold system, gold and silver, and a modern analogy would be the Yellowstone Park hot spring system. You see a geyser here surrounded, coming out of a conduit, and being surrounded by a pool of hot water and silica that's being deposited. Call that a Sinter pool. So this is what happens at the surface of what we think gold deposits, these low sulfidation gold deposits look like. Much deeper where there's boiling along the structures, we get these banded veins that can be extremely high grade, such as this bonanza grade gold and silver specimen here from the Hishikari mine in Japan. So I'll be using some forward-looking statements because we're talking about theories of how these things form, and I'll be talking about some of the evidence from these deposits that are actually pretty wide spaced around the world, so there is quite a bit of data on these, and then going into some details on the Highland project in particular, and why we're so excited about this project. El Peñon is an excellent example of a low sulfidation system. Very high grades, very high margin, relatively small mining footprint, and environmentally these deposits typically are very attractive. They tend to have very clean ores, and because they're fairly small size, they disrupt much less ground than, say, a large open pit. From an exploration standpoint, they're very exciting because once the structural controls are understood, then discovery of new deposits usually occurs pretty quickly. So on the right-hand side of the slide, you see in 1996, 1998, and 2001 how the resources, number of deposits grew very, very quickly. As I said, once it went into production, the cost of gold was quite low. The production costs in 2001 was $43 per ounce of gold, and in part that's because it's a very high grade, 17 grams per ton. Very attractive deposits indeed. Another great example is the WKP project in New Zealand. It was recently discovered by OceanaGold, and as you can see from the intercepts listed here from one of their news releases of September of 2018, these are very nice grades and decent thicknesses. They continue to announce similar type intercepts, and it looks like this is going to be quite a nice addition to the Marta Wahi mine complex. Closer to home, we have an example of a low sulfidation system at Wind Mountain. It's part of Bravada's portfolio of projects. The picture on the upper left-hand side is from a master's thesis in 2014. It is a sample collected from the bottom of the pit, and what you see there in black is a silicified sediment horizon that's cut by a number of fractures. Those fractures have iron stained along the margins. That's the sort of reddish to greenish colored things. And on that particular black area, outlined in black, that was cut out as basically a plug. It shows two of those fractures cutting through, and on the picture to the right, we see that iron stained area. So what was done for the thesis is a laser ablation study, but basically what that does is it takes point sources and analyzes those points across it, basically mapping out where different elements occur. On the picture to the far right, on the upper right, you'll notice it's labeled as gold. Basically the color scheme is the concentration at that particular point source. And you can see that it matches quite well with the iron stained area where the highest gold is. So the blue color is equivalent to about 0.1 ounce per ton, about a half an ounce per ton in yellow, and 1 ounce per ton in the red. You see the same feature on the lower left in silver. Very, very high silver concentrations along that rusty fracture. The yellow area is essentially 100 ounces per ton. Other elements show the same sort of pattern. So what this tells us is that in between these fractures in this densely silicified sediment, basically the fluids were not allowed to soak into the rock, and so the high concentration of gold with the fluid basically precipitated along those fractures and form the high grades that we see along those fractures. Basically, the more fractures you get, the higher the grade you would get. We'll now turn our attention to the state of Nevada that you can see in this slide, and the Highland project in particular along the western margin. Now this is just one of several low sulfidation systems that Bravada has in their portfolio. Wind Mountain, we just saw a slide from the bottom of the pit there. The Baxter project is similar, and so is the East Manhattan. So this information I'll be giving is somewhat applicable to these other projects as well. The remaining projects are generally Carlin type systems that we've acquired. This is a cross-section showing what we think happens as these gold deposits form, low sulfidation systems. The metal-rich fluids come from some depth, and as they move up, gold becomes unstable, drops off at some level. The fluids continue to move, spread out as they get into less and less confining pressure, and in some cases come to the surface, forming hot spring systems and potentially geysers, that sort of thing. Typically, the fluids are depleted of gold at this point, and so part of the technique that we've looked at is where these Sinter conduits are and whether those structures can be followed at depth to the area where gold is deposited. Now, erosion typically doesn't preserve these in their entirety, and on the western part of Highland, and for example, in the western vein zone has been eroded fairly deeply into the top of the main veins system. So Sinter is gone at this level. On the eastern side, where there's less erosion, Sinter is preserved over large areas, and we'll talk about some of the Sinter features that we've identified. The reason this is important is that in the western zone, where we are seeing deeper into the system, we see some quite good gold values. Our best intercept in one of our drill holes in 2013 was 12 meters of over 7 grams and over 100 grams of silver, and included some narrow zones over an ounce. So very exciting as far as an indication that this is one of the systems that can be very, very productive. This is a cross-section of the showing the intercept that I just talked about, and as you can see, this is a fairly small pot of mineralization. What's interesting is it's quite high grade, and it's pretty common in these sort of systems to get these little spurts out that are basically sampling what the ore fluid was capable of. So although this is not likely to be a deposit on its own, the trick is to find where the proper structural setting is where a large amount of this kind of grade can be accumulated. The inset that I show on the upper left-hand side, showing the A vein, shows some of the textures. This is fairly typical of what the top of a low sulfidation vein looks like: banding, brecciation, lots of quartz after calcite. So it's an indication we're above the vein, we're getting some good grade. So where is the the massive accumulation that's going to turn this into an ore deposit? And there are a number of things we can look at. We can look at flexures in the veins, we can look at intersections of the veins. Oftentimes the rock contrast between two different units. For example, here I show the unconformity target. This is the difference between basically very solid metamorphosed Paleozoic sediments and then the unmetamorphosed tertiary andesitic volcanics sitting on top of them. That sort of an unconformity is typically an area of weakness. There may be significant fluid flow along those channelways, and that's often where the best mineralization is. At Hishikari, for example, that's one of the major ore controls. We focused most of our work on the Highland project in the early days on the western part of our project, and you can see why. The symbols there in magenta are over 2 grams of gold up to 49 grams of gold, and you can see the majority of the samples are from the western area. This is because erosion is deeper in this area, exposing deeper portion of the system. As we did additional work, we recognized that we were on the edge of a graben. We call this the western graben. But we did recognize on the eastern area, we had a large area of Sinter float. And now we're trying to understand that. And that was the focus of Oceana's work during 2019. This figure is from a very interesting study from the University of New Zealand, in part funded by OceanaGold. What they did is they investigated modern hot spring systems that are associated with geothermal power plants on the island, and then a nearby parallel zone of gold mineralization that's quite a bit older, but a very significant amount of production, over 10 million ounces of gold and 48 million ounces of silver. There are more than 50 low-sulfidation deposits along this belt. And so what they've done is they've looked at the features that are preserved in these sinters that have come to the surface and been preserved. Thermophiles, in other words, little microbes that grow in these kind of environments. And what they can see is that there's a zonation between where the hottest part of the system is, basically where the conduits are in modern systems, and then migrating outward until the edge of the system, the edge of the Sinter pool, and out into the surrounding forest. They found this both in the modern system, which of course you can see because you can measure the temperature of the water, but also in the fossil system, which had fossils that really hadn't changed in over 16 million years. We have found these fossilized thermophiles and textures in several of our projects. Highland and Wind Mountain have some of the best examples. You can see the bubble mat up in the upper left-hand side. This is where basically mud was boiling. It was still so hot. Moving farther outboard away from the heat source, we see palisade textures. That's that sort of fibrous looking material on the right-hand side of the Highland projects. Farther out, the silicified reeds, in this case in the growth position from Wind Mountain. This is typically the edge, the marshy edge of the hot spring system. It's hot, but it's not hot enough or too hot for plants to live. And then some features that grow outward or are formed outward, including logs off to the edge of the hot spring system. Usually in these type of systems, the conduits are not preserved. They're broken up, they're brecciated. But we believe we found one at the Highland project, and that's the upper left-hand slide there. Those stakes there are 4 feet long. To the right of that, and very close by, about 20 meters away, is a very, very thick section of sinter. Again, the same 4-foot zone, so it's about 2 meters of total thickness of the sinter in that area, finely laminated. And being close to this structure is having identified the structure where the hot water came to the surface is important, because by chasing that with depth, presumably we can get to the point where banded veins could have developed, and potentially high grades of mineralization could occur. So where are the structures where the fluids would have migrated to the surface? One feature that you see often with the low sulfidation systems is that they're related to extensional structures. In other words, where the ground has been pulled apart. We call these grabens, and often the margins of the grabens are where much of the structures have developed, and that's oftentimes the migration path for gold. This is the Republic District in Washington and extending up into British Columbia, and a number of deposits that have been mined in the past, some very good grades as well. And now back to Highland. On the eastern side of the property, the slice or strips that you see there, those are CSAMT lines, and basically what they've shown us in this geophysical method is where a graben is formed. The dark purple and hotter colors are indicative of the graben margins. Farther to the north, we see the southern edge of the Desitoya caldera. This is a feature that formed quite a bit older. It was around 24 million years ago, as opposed to likely 16 million years for the mineralization. On the west side of the project, on the southerly two lines, you see some purple as well, and that's just picking up the edge of a graben that we've identified based on some AMT geophysics as well as some mapping as well. There's mineralization associated with that western graben, and there's mineralization, we believe, that's related to the eastern margin. This slide shows our targets relative to the geologic features that we've been discussing. The eastern graben is an important feature because it does control of the large area of Sinter development. The Big Hammer target area is of particular interest because it shows there's a heat source there, as evidenced by the flow dome complex that's preserved. There's strong gold mineralization in the area. We've gotten some pretty impressive gold samples, 1 to plus 10 grams, and it appears to be a very large feature. We'll be conducting our initial drilling program just to the east of the Big Hammer target, and we'll be conducting some surface geochemistry mapping, clay studies at the Geyser target, which is of interest because that's where a conduit has been identified in the center, and presumably we'll be able to chase that structure down to depth where gold, high-grade gold, would have deposited. As we announced earlier, Bravada will be conducting the field work, which will be funded by OceanaGold. We began our field season with staking the open ground that we recognize as having potential based on the CSAMT data, and we will be somewhat postponed due to the COVID-19 pandemic in conducting some of the other detailed field work that we had anticipated. We should be able to get that work done early in maybe mid-May and get our results back, choose our drill sites, get that permitted, and hopefully we'll receive our permit by the end of August. We anticipate drilling 2 core holes, 1 to 2 core holes, depending on the depth, and that will be basically in the area just east of the Big Hammer flow dome complex. That's also the western margin of the eastern graben. So there's good gold values. There's a heat source as evidenced by the flow dome itself, and the structures show up very well on the CSAMT image. There's actually two structures, and our hope is to drill test both of those. We'll also be doing some field, just some surface work on the Geyser target. That's the conduit where the hot springs came to the surface. There's also fairly good exposure, subcrop and outcrop of the host rock underneath the Sinter horizon. Very strongly clay altered, and I think geochemistry and clay mineralogy could be a good indication of and provide us with vectors to gold mineralization that's related to the same structures that guided the hot springs fluid down at depth where high-grade gold was deposited. We know that low-sulfidation deposits make some of the best mines in the world. I've tried to show here, that Highland has many of the important features that we see in these deposits. I've also tried to show that new knowledge about these deposits has given us the information that we need to predict where we can find blind deposits. And these deposits haven't been discovered and are completely preserved underneath, for example, the Sinter, which we know is barren. The old timers would not have paid too much attention to these deposits because, of course, the gold had been depleted in the fluids before those fluids reached the current erosion level. I also want to note that our partner, OceanaGold, is very well versed in these type of deposits, and for them to earn a 75% interest in Highland, they must make expenditures of $10 million. So we're off to a good start for 2020. We'll do an initial round of drilling, and hopefully that will lead to much more drilling in 2021.